Hi guys, in this lesson on circular motion, we're going to be looking at complex derivations. Now, in our previous set of lessons, we perfected everything on basic, derivations of various formulas on circular motion. We derived the formula for, for different things: angular and linear displacement, angular and linear velocity, angular and linear acceleration, and then we went to derive the formula for centripetal or angular force alongside the period. Today we're going to be looking at a couple of complex formulas on circular motion. So now look at what we're going to be dealing with. Today we are mainly talking about uniform circular motion, UCM. We're not discussing non-uniform circular motion. We're only discussing uniform circular motion. So under the uniform circular motion, we're going to be talking about horizontal circle, and after that we talk about vertical. We discussed this already. Circle. So under the horizontal circle, we have a couple of things we're going to be discussing. Under it, we're going to be discussing, we're going to be discussing canonical pendulum. We're going to be discussing the canonical pendulum. Then we're also going to be discussing this under horizontal circle. Canonical pendulum. We're also going to be discussing a car moving on a plane circular path. A car moving on a plane circular path. We're going to be discussing that. And after that, we're going to be discussing also a car, maybe anything. A car moving on a banked circular path. Now, we can use this, there's another scenario that looks like this, which is a bike rider, either a bike or, bike. When you talk about bike, you're talking about a bicycle or a motorcycle rider. A bike rider moving in a circular path. So these are the formulas. You're going to be deriving various formula for all the scenarios. First of all, canonical pendulum. Next, a car moving on a plane circular path. Next, a car moving on a banked circular path, or a bike rider moving in a circular path. While for vertical circle, we are going to mainly be talking about the Ferris wheel. The Ferris wheel is what we are going to be mainly talking about. The Ferris wheel. So we're going to be using the Ferris wheel to discuss the vertical circle, or we're going to be using all of this to discuss the horizontal circle. So to start with, we're going to be starting with the canonical pendulum. Okay, how do we use the canonical pendulum to explain uniform circular motion? To be precise, horizontal uniform circular motion. Now there's it here. Don't forget we are deriving formulas on this. So we talk about canonical pendulum. Now there's it as more or less like the normal pendulum, but look at what it looks like. This a canonical pendulum. We have this here. We have the bulb, the pendulum bulb at this very junction, being connected to this place. Now the pendulum is being weird like this. It moves in this circle. Goes this way. The pendulum goes this way, just like this. It's weird like this. Now there's something like this. There's a radius of the circle here. Now don't forget this is a string. The string makes an angle of theta with a vertical. So this pendulum here has a weight, a downward weight. Weight is mass times gravity. Look at this. This weight is a kind of force also. So the weight is mass times gravity, while there's the length of the string of the pendulum. So the pendulum oscillates like this in what we call horizontal cycle. Don't forget, the canonical circle talks about canonical pendulum, I beg your pardon, talks about horizontal circular motion. So it's horizontal circle. So now what are we going to do here? We are going to derive various formulas on this in case we see questions on this. So now there's it here. We have the length of the very string. Y here is the radius of the very circle. So don't forget the string. There's a tension in this string. There's a tension. Now the question is, what brings about the circular motion? Now don't forget something. For horizontal circular motion, gravity is not really involved. Although we have force of gravity actually, but gravity is parallel. Not perpendicular. Gravity is parallel to this. So the force of gravity doesn't really have any relationship or does not play any role in the circular motion. What brings about the centripetal force here, that is the force that keeps this body moving in a circular path, is the tension in this very string. It's a tension. It's a tension that makes this body to keep oscillating. It's not gravity. So now, how do we explain that? We're going to explain that, and also we're going to derive formulas for this. So first of all, you have a tension here. The tension is going to, since this is an angular motion, the tension will be resolved in two dimensions. So first of all, we have the tension like this. This tension. We need the help of trigonometry here. You have to have the basic knowledge of trigonometry, trig ratio. So we have an angle here, theta. So we have a force, the tensional force, this Ft is the tensional force. The tensional force along x-axis, the tensional force along y-axis. And for the fact that the tension is facing up like this, the component to be resolved in these two components, like this and like this, as simple as that. So now this is going to be Ft over tension, opposite, hypotenuse, adjacent. SOHCAHTOA, very simple. So opposite over hypotenuse is sine, that's sine theta. So we have Ftx equals to tension sine theta. That's that. So the next Fty, you know what it is? Fty is adjacent hypotenuse, which will be tension cos theta, according to SOHCAHTOA. You need the basic knowledge of trigonometry for you to understand what we are taking. But this is this set of derivations are more complex derivations. They're not like the other ones. So now what do we do next? Now we're going to be getting some of forces along x-axis and along y-axis. And don't forget, you're working on the tension. The tension, since this is an angular movement, and don't forget, circular motion is two-dimensional motion. Since this is angular, the tension is resolved in two dimensions along y and along x. So now what's the next thing? Since we have a tension force like this and another one like this along x-axis, why there is a weight, acting downward. So the sum of forces along y-axis is going to be mass times acceleration along y-axis. Now, is there any acceleration along y-axis? There's no acceleration. The body is not moving up and down. The body moves in a circular path like this. So the only acceleration we have is acceleration along the x-axis. There's no acceleration because the body is just moving like this. The body is not going up and down. So what do we have? Some of forces along y-axis. What do we have? We have the tensional force, Fty, minus the weight, which is mass times acceleration. Acceleration is 0 meter per second squared along y-axis, no movement along y-axis. So what do we have here? We have the Fty minus the weight, which is mass times gravity, equals to 0 Newton. So we send this to the other side. Fty is equals to, this is what we have. So as simple as that. Fty, that's the same tensional force along y-axis. Apart from this, is mass times gravity. So let us now look at what sum of forces along the x-axis. Sum of forces along the x-axis will give us mass times acceleration along x-axis. So now if you look at the major force we have along the x-axis is just the tensional force along the x-axis. Although there's movement along the x-axis, it's the tensional force along the x-axis that we have. There's no other force here. We only have force along the tensional force along the x-axis. So now, what's it going to be? Sum of forces will be the tensional force along x-axis, just this, no other force really. Then times that's mass times acceleration along x-axis is going to be, don't forget, acceleration along x-axis is centripetal acceleration. That's what it is. So acceleration along x-axis is centripetal acceleration. In our previous class, we use alpha. We use alpha to represent it. So centripetal acceleration, which is written as v squared over r. That's what it is. So this acceleration, that's going to be mv squared over r. So that's what it is. So what do we have? Tension along x-axis is mv squared over r. That's the only force along x-axis, the tensional force along the x-axis. Now we have this already set out. We have this set out. So now you're going to compare the two sets. We have this mv squared over r, and don't forget r is the radius of the circle, while we have this mass and gravity, that's tension along y-axis. And don't forget we also have ft sine theta and ft cos theta. So what we do next, and we're going to bring them together, we're going to integrate them. So what do we have? That's what we have. Right here, ft, that's ft, tensional force along x-axis over tensional force along y-axis. You know what it is? That is ft sine theta over ft cos theta, which is equals to, what do we have? Ftx is also mb squared over r over that, what do we have there? The other one, just mg. Now, tensional force takes out each other, so we end up with sine theta over cos theta, which is tan theta equals to, what do we have? mb squared over r times 1 over mg. So mass takes out mass. So what do we have? Tan theta, which is the angle of this movement of this whole movement, equals to v squared over gr. That's what we have. Now, this v could be termed max velocity. The v here, we could say the v here is the maximum velocity, the maximum speed for this whole circular, motion. So what we're going to do next is you're going to go up there. Formula is quite lengthy. We're going to go up here to finish up the whole thing we started. We're going to go up there. So what do we do next? So since we have tan theta equal to v squared, so tan theta equal to v squared, you can say the v is the mass speed over gravity times radius. So what it means is that v squared is gravity radius tan theta. So v is square root of gr tan theta. So the maximum speed, the highest speed, or generally the speed, that it takes this given body, the speed with which this body covers the circular motion is gravity times radius times tan of this angle, the angle, this length, the length mixed with the vertical. Now that is one major powerful formula, very important. This one also is very important. You have to know that. So we can also come up with something. If you look at this length, the length, look at what we have here, the length of the string. Here's the length here, the length of the string. Here, right here is the radius, this angle. So this is upward, this opposite hypotenuse. So the radius over length equals to sine theta. So the radius is length sine theta. So we could also have this. So we could also substitute this into this, which will give us a new formula, which is gravity. Radius is L sine theta tan theta. So yeah, all the formulas we have. This one of them, we have this gr squared of. So the maximum velocity in a canonical pendulum is gravity times radius times tan of the angle. Also, the maximum velocity is also, square root of gravity times length of the length of the string, then times sine of the angle, tan of the angle. Yeah, simple as that. Or it could also be this tan of the angle is square of the linear speed over gravity times radius. Whichever one we want, they are all they're all useful. So that's everything for this canonical pendulum, and it's everything for the first phase of complex formulas on circular motion. So we draw the curtain on this very lesson. So if you found this lesson resourceful, please follow me on Facebook at Revelation Up. Subscribe to the very channel at Edge Mosaic and share this lesson with others. See you in the next lesson. Thanks.